Modern data transmission relies on the elegant relationship between complex numbers and electromagnetic waves. Today we will explore this by understanding constellation diagrams, breaking down the codebook logic of digital modulation, and examining the IQ modulator's hardware implementation. Finally, we'll bring it all together by building a MATLAB-compatible script using Octave. To transmit data wirelessly, we rely on electromagnetic signals, which can be pictured as simple sine oscillations. However, a static, unvarying cycle is empty. It carries no information. To pack it with data, we must shape the wave. The two key properties we can modify are its amplitude, the signal's peak height or power, and phase, its position in the cycle. Before transmission, the two devices agree on a codebook, a mapping that links specific combinations of amplitude and phase to bit patterns. For example, an amplitude of 1 with a phase of 45 degrees might represent 0, 0. The same amplitude with a phase of 225 degrees could represent 0, 1, while an amplitude of 0.5 with phases of 315 degrees or 135 degrees could represent 1, 0 and 1, 1. When sending data, the transmitter slices the stream into chunks, here 2 bits at a time, and modulates the wave according to the codebook. The receiver, using the same codebook, observes the wave's changes and reconstructs the original bits. And now here's the conceptual leap that powers modern communications. Instead of juggling two separate properties, amplitude and phase, we can represent each state as a single point on this 2D plane. And mathematically, a point on a 2D plane is perfectly described by a complex number. Think of it like this. The distance of the point from the origin, the absolute value of this complex number, gives us the amplitude. The angle the point makes with the axis, the angle of the complex number, gives us the phase shift. By specifying just two coordinates, I and Q, we are implicitly defining both the amplitude and the phase. This complex number becomes a complete instruction for the transmitter, telling it exactly how to shape the carrier wave. So how do we actually create this modulated wave? That's where the brilliance of the IQ modulator comes in. The transmitter takes our two values, I and Q, and sends them on two separate paths. The I component, the real part, is multiplied by a cosine wave. The Q component, the imaginary part, is multiplied by a negative sine wave. This is the same carrier, but shifted by 90 degrees. Finally, these two signals are added together. Thanks to trigonometry, their sum forms exactly the wave we wanted, one with the precise amplitude and phase set by our original complex number. This abstract IQ concept solved a real hardware problem. Rather than building complex phase and amplitude controllers, we use simple multiplications and addition, operations that are easy to implement in both analog circuits and digital processors. Now let's move on to the second part of the video, where we'll compare these two modulation methods in simulation. You can find the code linked in the description below. We'll start by defining the parameters, beginning with the constellation. For this demonstration, we'll use a set of basic randomly selected values. However, in professional communication systems, these symbol locations are engineered with precision to minimize the chance of errors. If you'd like to learn more about that, check out the video on digital modulations. Next, we map specific bit patterns to each constellation point and build a code word, a stream of bits that the transmitter will send. Once you have the script, you can experiment with your own custom sequences to see how different data patterns are mapped onto the grid. Finally, we visualize the result with a constellation diagram. As you can see, the plot reveals 4 distinct points on the complex plane, each serving as a unique digital signature for its assigned bit combination. Now let's dive into the signal modulation process. First, we establish a sampling frequency of 1000 Hz and generate a 4-second time vector, allocating exactly 1 second for each transmitted symbol. Next, we identify the corresponding symbol indices by comparing each bit pair in our bit stream with the codebook we defined earlier. This step allows us to map raw data to specific complex symbols based on our initial constellation map. The first method we'll demonstrate is direct phase shifting and amplitude scaling. For each symbol, we select its time segment and calculate the phase shift based on the symbol's angle. Then we generate a cosine carrier and apply the calculated phase shift. Finally, we scale the carrier by the symbol's amplitude. This gives us a properly modulated segment, which we place into the overall transmitted signal. Next, let's look at the second method, which uses IQ modulation, the approach explained in the theory section. We define two carrier signals, a cosine wave for the I component and a negative sine wave for the Q component. To ensure the symbol and carrier vectors match in length, we repeat each transmitted symbol 1,000 times. We then modulate by multiplying the I components, real parts, with the cosine carrier and the Q components, imaginary parts, with the negative sine carrier, then add the two results together. Finally, we plot the outputs. As you can see, both methods produce identical waveforms. The second method is much easier to implement in hardware, which is why it's the standard approach in real communication systems. And that's it for today's breakdown. If you want to learn more about constellation diagrams and digital modulations, check out next video in the series on quadrature amplitude modulation. Thanks for watching.